I hope you have fun. I also take the opportunity to take some break. Okay. Now we are done with the driving point. Now we already start looking at the first amplifier, how to analyze. But that one, early T, is for BJT. Okay, because in early days, BJT actually have faster response compared to MOSFET. But let's look at the MOSFET. So for MOSFET, this is actually equivalent to BJT early T. You will see BJT and MOSFET, a lot of time the circuit is interchangeable. So for this guy, if you look into the input, you see infinity. The output resistance, you look into here, you will see RD parallel with R0. So it's the same thing. Now for the gain, we didn't have very complicated biasing network. If you have biasing network, it's not that difficult to figure out. But here, the Vin directly appear at the gate. So right away, it modulate the current source. So there's a GM here. And then the total resistance, I told you, looking at the output node, turn around 360 degrees. You will see the RD, and then you will see R0 parallel. So you can write down the gain in a very simple manner. Negative sign, you probably don't know why negative sign, but just remember this is the final result. Now to explain briefly why there is negative sign, the current source is actually given by GMV in. But the resistor is actually this guy. So if you look at the output voltage, the current actually flow in the anti-clockwise manner. Right? Yes or no? The current direction is determined by this guy. This guy tells you going down. So the current actually flowing in anti-clockwise manner. So if this is positive, this should be negative. Because for resistor, the current can only flow from higher potential to lower potential. Right? The higher potential is already 0. So the lower potential has to be negative. So that's why there's a negative sign. Now, we have the input connected to the base or the gate, output coming out from the collector or the drain. Let's look at the second scenario. Input connected to the emitter or the source, output coming out from the collector or the drain. So the first one is CB. The second one is CG. So let's look at the first one, input resistance. You look up. If you know the driving point, should be quite easy to figure out. You're looking up into the emitter, so right away 1 over GM. There is a resistor RC connected to it, so you're going to have R0 plus RC, R0 divided by R0 plus RC over beta. If you further assume RC is usually small, so ignore this, then the whole thing reduced to 1 over GM. R out is looking into here, so you're going to have RC parallel with the resistance looking down into the collector terminal. So that one is given by what we derived earlier, R0 multiplied by 1 plus GM multiplied by RI parallel RS. Okay? And the voltage gain, again, starting from VS, let's figure out V1, which is a simple voltage divider. So as long as you figure R in, you can write down this guy. And then with this guy, once you determine V1, you determine the current source, which is GM. And then finally, what is the total resistance over here? You look 360 degrees, you see RC parallel with this whole thing. But this whole thing is so big, RC is smaller, it's going to be dominated by RC. So I only write down RC over here. So we can see in circuit analysis, we make use of intuition, we make use of formula, okay, and we can easily derive the result. Some of you probably already complaining, this is not accurate, everything is approximate. But that is exactly my point, right? Why do you need accuracy? You just need to have the ballpark figure, some rough idea, what is the range. If you need accurate result, you have cadence. Nobody is going to design based on hand calculation. All the fine-tuned result is based on cadence. But where do you start? From hand calculation. You want to see whether I can get a gain of between 100 to 200 possible. Then you start designing in detail. Right? Now, let's go through common gate first before I try to analyze this type of amplifier. So same thing, input resistance, looking up. Looking up, you're going to apply the formula. So roughly about 1/Gm minus GMB. We derived that result before. Output resistance is going to be RD parallel with this whole thing. That is very big, so we can ignore. And then the voltage gain, we go through the same analysis. To determine V1, we can use the voltage divider, since there's no Rin. And then that will give you the current cell, so Gm minus GMB. And then finally multiply by the total resistance, RD. So we can derive this result easily. Now, one thing you'll notice is that the gain is actually very similar to common emitter and common source case, which is this guy. Okay? If you compare this guy, you see, this is the gain. If you compare the early T, you see, this is the gain. I don't really care about this guy because usually this can be designed to equals to 1, right? So the gain is very similar to common emitter, common gate. Common emitter, common source, sorry. The only difference is that no negative sign. No negative sign. In fact, it will always give you positive gain. So this is one of the good thing. No polarity inversion. There is another good thing. No Mueller effect. No Mueller effect. Because there is no capacitor that directly connected between output and input. There is a parasitic capacitor between collector and base, but there is no capacitor between collector and emitter. There is capacitor between gate and drain, but there is no capacitor between drain and source. Okay? So there is no Mueller effect. That's good. So we already covered two good things. There is another even good thing. Impedance matching. You notice that the impedance is given by 1/Gm, and the other is 1/Gm minus GMB. If you know the value, these two usually is not big. A few tens ohm to a few hundred ohm. And this make it ideal to match to antenna. Antenna is 50 ohm. TV antenna 75 ohm. Right? Some people design matching network. So with 50 ohm, after going through matching network, it gives you a resistance of 200 ohm. Right? 1 to 4. So all this tells you in RF, input resistance is never big. And this guy gives you a way to exactly match this impedance. Any one of you know why we need to match impedance? Anyone? Maximum power transfer. Okay? In normal voltage amplifier, right? A lot of students confused. I'm confused by the circuit lecturer. Sometimes they talk about maximum power transfer. Impedance need to match. Sometimes they talk about voltage divider. Resistance need to be maximized. Why? Because you are dealing with different kind of source. When you are dealing with RF, you are absorbing power from the antenna. You are dealing with power source. So for power source, you want to maximize the energy you can extract. Therefore, you need to use maximum power transfer. Right? That is RF. Now, if you are talking about normal signal in the lab, let's say audio signal. The audio signal source, you want to maximize the voltage that gets transferred. You don't care about power. I just want to get this voltage amplitude. I don't want to attenuate it. I want it to maximize, transfer over. Then you want the input resistance to be infinity. In that way, you don't have any attenuation. You get the point? So in that case, you are dealing with voltage signal, not power. Therefore, we maximize the resistance. So everything comes down to what kind of source are you dealing with. Okay? So to answer you, it seems like this guy, everything is good. Impedance matching, no polarity inversion, no Mueller effect. Everything is wonderful. Why people still need common emitter, common source? Because let's say for voltage amplifier, this will not be good. Am I right? Because the impedance it presents is very small. So there is no 100% winner. Common collector. So for common collector, you connect the input to the base, output coming from emitter. We can use a simple, intuitive circuit that we derived earlier when we try to come up with the reflection rule. So we told you already, between V in and V out, I can consider it like one side I have a Ri, the other side I actually have 1 plus beta RL. The reason, one side I have current IB, the other side I have current beta plus 1 IB. So instead of putting the beta plus 1 associated with IB, I associate 1 plus beta with RL. You get the same point? The same thing? Same thinking here? Let me repeat. The current here is IB. So I know this is IB. In fact, the current here is beta plus 1 IB. Okay? So the voltage drop here is actually given by beta plus 1 IB multiplied by RL. The voltage drop here is given by IB multiplied by RI. But you know it's algebra manipulation. Whether I associate this guy with this guy, or I associate this guy with this guy, it doesn't matter. Am I right? When you multiply A multiplied by B multiplied by C, it's the same as B multiplied by A multiplied by C, isn't it? Right? So let's change this. Move the IB in front. And I have this term. So equivalently, I can treat this network as only have one current, IB. But I'm seeing different kind of resistor. Ri is series with beta plus 1 RL. Okay? Now if you do this, then you would be able to derive V out in a very easy manner because it's voltage divider. This is the resistor at the output divided by the total resistor. Okay? Eventually you end up having this guy. Okay? So common collector. That is how we derive the result. Some people also call it emitter follower. This kind of amplifier, it only have voltage gain of 1. Okay? But it's an ideal impedance transformer because you know that the output resistance is actually very small, but the input resistance is actually very big. Okay? So this is very ideal buffer amplifier. Okay? Common drain amplifier, something similar. Even better, input impedance infinite. Output impedance 1 over Gm minus Gmb, also small. Now to derive the equivalent, we cannot use the just now that rule that we talked about for BJT. So we have to go back to the fundamental, okay? But we can easily derive it. The current source for this guy plus the current source for this guy, okay? And then multiply by these two resistors in parallel will give you V out. So after some manipulation, move V out to one side and then keep V in on the other side. And then you try to derive V out over V in, you get the following result. And eventually, something similar to this guy. Okay? So again, no big gain, and it's going to have close to unity gain. If you have twin well process, so you know NMOS, the body always have to connect it to ground. But twin well process, we are going to create the so-called P well, sit on top of deep N well, and this guy sit on top of P substrate. So this guy you are going to have N plus, P plus. So for this kind of NMOS, your body can always be tied to the source terminal, and without being worried that you are going to forward bias the transistor. Okay, that is what we call twin well process. Why do we call it twin well? You have the deep N well and you have the P well. Okay? More expensive. So usually people don't do that. Research, we don't care. Research, we don't care. But industry people, they try to avoid that. Now, compared to BJT, it's poorer in two aspects. One is that the gain is never unity. It's in fact smaller than unity. Now, don't be fooled by this negative sign. GMB is actually a negative value. So GMB is approximately equals to 1/4 GM, negative. So in fact, what you're going to have is GM divided by 1.25 GM. So therefore, you end up having about 0.8. Okay? So it's actually smaller than 1. The second inferior property is that GM for MOSFET is only proportional to square root current. But GM for BJT is proportional to collector. So you can get much larger GM for BJT using the same current compared to MOSFET. So therefore, BJT is actually a better buffer amplifier. In fact, buffer amplifier is also known as power amplifier. So you will know that a lot of time power amplifier, people prefer using BJT. Right? So CGAT, silicon germanium, HBT, by CMOS. Why people like this kind of process? CMOS good for digital, low power. But bipolar, power amplifier. So together they can build R chip, everything self-contained. Okay? We stop here. When do you want to resume? 7:50, 20 minutes. Is it okay? Okay, so look at the clock, 7:50. Okay, let's resume. When you talk about amplifier, one of the concerns is that when the amplifier can be used. In fact, all those analyses like driving point or the gain analysis, all this is based on the assumption small signal. You know the transistors are nonlinear, right? They are nonlinear. The reason we treat them linear is because we assume they are only vary over a small range. But what kind of small range is considered valid without introduce too much distortion? Okay, so let's look at the BJT characteristic. So you know BJT characteristic is exponential. Now we can split the voltage into the DC term and also the AC term. Okay? Now the DC term we can lump them into a constant number, and then this is the AC term, small term. We can further split this small term, exponential x. If we recall, exponential x can be expanded using Taylor series. And it can be expressed in terms of a bunch of polynomial, x squared, x cubed. And if the x is small, I can throw away all the high order term and only keep this guy. And this would be considered a good linear approximation. But that is under the assumption x has to be much, much smaller than 1. Now usually much, much smaller, a rule of thumb, let's say less than 0.1. 1/10. If x is less than 0.1, that is considered much, much smaller than 1. What we have is VBE over VT much, much smaller than 1. So which means VBE has to be much, much smaller than VT. So if we want to make sure is 0.1, then it means your VBE better to be smaller than 0.1 times VT. So what is your VT? VT is terminal voltage. Very famous value, 26 millivolt. So which means your VBE that can apply to your circuit and is still valid cannot be larger than 2.6 millivolt. That is very small. Am I right? Very small. Any signal bigger than that, you are going to see square term, cube term. There is a lot of distortion. Okay? Now, how about MOSFET? MOSFET, we still use the long channel, easier for us to understand. So we can also split the current component into the DC and the AC. And we can split the voltage into the DC and the AC. If we first further expand them, we see that we got the linear term. The first term is just constant, which is the offset. We don't really care. Second term is what we want, linear term. The third term is the nonlinear term, square term. Now, if you want to make sure everything works linearly, you just need to make sure the linear term is much, much bigger than the square term. And this is happening if the VGS is much, much smaller than this guy. And VGS minus VT, we usually have a name for it. We call it gate overdrive voltage. Gate overdrive voltage. And this turns out to be much bigger than 26 millivolt. So MOSFET is better than BJT from two perspectives. One is that it can tolerate larger range without too much distortion. Second perspective, if you look at the equation, they only introduce square term. Unlike BJT, they will introduce cube to the power 4 to the power 5th. So there's a lot, much more distortion for BJT compared to MOSFET. Okay? So in fact, if you look at those those guys who are very crazy about audio amplifier, they claim they will build amplifier using MOSFET. Okay? And this is better than BJT. And some claim they will build using vacuum tube, because vacuum tube is better than MOSFET. Okay? So they are very crazy about this kind of distortion and noise. Now, knowing the signal range, then it brings us to another slight variation of amplifier. We call it degeneration. Emitter and source degeneration. Now, the structure looks very similar. You just insert a resistor at the source terminal or the emitter terminal of the transistor. So we call this guy common emitter with degeneration or common source with degeneration. In fact, this is some sort of local feedback. We mentioned that before. You insert the resistor, you are providing a feedback to the input in series feedback. And the good thing, it boosts the impedance. That is one thing. Second thing, it improves the linearity. Okay, improve the linearity. Feedback improves linearity, you all know. Now, from the BJT perspective, that can be easily understood. By inserting the resistor, your Vin no longer appear purely on the base emitter junction. In fact, only a small portion appear at the base emitter junction. A large proportion is appearing across the resistor, RE. And since, let's say, previously you can only tolerate 2.6 millivolt. Now, since this 2.6 millivolt, only a small portion appear over here, now you probably can tolerate 26 millivolt. Because only a very small portion appear across the VBE over here. So how much it can tolerate? We will talk about that later. RE, we already covered that. It will boost the input resistance by this factor, 1 plus GM RE. For output resistance, it will also boost it up, but eventually it's limited by RC, the other parallel branch. Now, in terms of the GM, why do we call it degeneration? Because the current source is going to be divided down by a factor. And you can see the current source, GM, is going to be divided down by this factor, 1 plus GM RE. How do we derive this guy? We make use of the simple voltage divider. You see that only RI is appearing across this whole branch. So actually the whole VBE only occupy RI divided by the total resistor. That's how we get it. After manipulation, it's simplified into the following. Okay? Now for MOSFET, same thing. Input resistance, infinite. Output resistance, you can boost the resistance looking down into the drain terminal, but eventually it's limited by the smaller one, RD, in parallel. And then for the V1 is simply these two current sources summed together, multiplied by RS. Okay? And therefore we can derive V1 equals to V in multiplied by this factor. Now, what is GM? GM is basically how much output current divided by V in. But the output current is basically the sum of these two current sources. And we already derived V1. So you just substitute inside, you get the following. So there is the GM. Again, you notice that compared to common source, the GM is reduced by this factor, 1 plus GM minus GMB RS. That's why we call it degeneration. Degeneration usually means degrade. So for this kind of amplifier, it degrades the GM. It degrades the current, the transconductance factor. But this will lead to smaller gain, but it will help improve the linearity. How? So this figure gives an illustration. If you have a resistor inserted at the emitter side, you can lump this whole thing together and call it a new transistor. This transistor will have a reduced GM. Okay, compared to BJT, we have a lowercase GM. This new transistor have a lower GM. This GM is given by GM divided by 1 plus GM RE. Now, if this guy can only handle 0.1 VT, then this guy can handle 0.1 VT multiplied by 1 plus GM RE. Because effectively, if you reduce the GM by certain amount, you can boost the input voltage by the same amount. Okay? So, in graphical method, it means this is the original BJT. This is the degenerated BJT. What it means is, it makes the gradient less sharp. It makes the gradient more gradual. So what do you trade? You make sure that I can handle larger input without too much distortion. Okay, without too much distortion. So, does it really come free? No. You actually lose the gain. Okay, you just lose the gain to make it more linear. That is all it is. Now, for the MOSFET, same thing. You are reducing the GM by the factor 1 plus GM RS. So, effectively, you're boosting the range by this factor, amount of factor. Okay? So we have gone through all the driving point. I nicely summarize it over here. I think for those who have taken my undergraduate module, you probably have seen this table before. To use it, very simple. You just ask yourself, which terminal are you looking into? So if you are looking into the base, you know this is the result. If you are looking into the collector, this is the result. If you are looking into the base with some resistor inserted, this is the result. Okay, so on and so forth. So you can apply all these results accordingly. And this is the MOSFET equivalent. Now, I didn't show PNP, I didn't show PMOS because they are the same. Because remember how I teach you to use which terminal are you looking into. So for NMOS, you look into the gate. PMOS, you also look into the gate. As long as you're looking into the gate, you use the same formula. You get the point? I don't care whether it's NMOS or PMOS, they are MOS. I don't care whether it's MPN or PNP, they are BJT. I don't care whether you are a woman or man, you are human. Okay? So as long as you have same characteristic, gate terminal, source terminal, drain terminal, you can use the table in the same manner. Now, here I list down 4 amplifier, and then I also list down the corresponding GM cell. So we derive this guy, and also the voltage gain accordingly, if it is common collector. For MOSFET, same thing, we have the GM cell. We also have the voltage gain in terms of common drain amplifier. So with this 4 table, get yourself familiar. I always urge students, although table is given to you, by the way, the exam is open book. So you can bring anything, you don't have to memorize. But I always urge students, memorize. It's like when you solve the differentiation, do you go back to the thick maths textbook to find the equation before you solve it? Never, am I right? you commit to your memory, exponential x, sine x, cosine x. You never go back to the textbook. Once in a while, you might forget. You might forget, oh, sine x, is it negative cosine x or is it cosine x? You might forget. But it doesn't matter, you know the result, you write down. Later, because it's open book, you can check. Right? So same thing here. Although I never ask you to memorize, it's a good idea to memorize because it's spitting up. So we have done driving point. We have done single stage. Let's look at the interaction a little bit more. Two transistors combined. So what kind of interesting structure they can bring? How can I combine them and what are the advantages, so on and so forth. So let's look at the first one, very simple. Common emitter, common source. You probably can deduce. This guy, input resistance is the same as common emitter. Output resistance also same as common emitter. What is the only advantage? It boosts the gain. Right? If one stage got moderate gain, another stage got moderate gain, combined together, they can get high gain. So that is the only beauty. Now, for this one, deriving is quite straightforward. Input resistance, looking into here, you have RA1 parallel RB1 parallel RIQ1. So you got the following. By the way, let me stress again, Zoom session, I wouldn't admit anybody, okay, because it's only for recording purpose. I told you during my first lecture already, this module I'm not conducting online lecture. But for those who cannot join, I will release the recorded video. So there is not a problem. But I don't want to keep jumping around. Are you guys with me? And then later check the chat window. Are you guys with me again? Okay, so I keep it strictly physical, face to face. Okay, output resistance. Now, you no longer look at this guy. Output resistance, you look at the last stage. So you have the RC2 parallel with R02. Okay, RL, if you lump them together, you include the RL. Okay, now the voltage gain, this is a simple voltage divider. So you can see I use the voltage divider. And with this first stage Q1, I have the current cell. And with this current cell, I'll multiply the total resistance at which point? At this point. And you look 360 degree. You look 360 degree around this point. So you look to the top, you see RC1. You look to the bottom, you see R01. You look to the right, you see RA2. You look to the right bottom, you see RB2. And you look further to the right, you see RA2. So basically, you just at this point, the current cell, what are the all resistor, total resistor connected at that point. So once you get this point, you just turn yourself around 360 degree and you figure out all the resistor connected to this point. That is how you do it. Once you get this point, you reach Q2. Reaching Q2 give you another current cell, GM2. And then once you get the GM2, again, you reach this output point, you turn 360 degree again. So this 360 degree allow you to see RC2, look down, R02, look to the right, RL. And therefore you can easily write down the whole gain. And of course you can simplify. If you usually as a designer, you probably can choose. I can make RI2 dominate. RA2, RB2 is what you pick. R02, R01 is big. RC1 you can also pick. So if you pick the resistor very big, then eventually dominated by RI2, the whole thing simplified to RI2. Okay? And then at the output, if you pick RC2, R02 relatively big, then everything limited by RL. So you can simplify the gain accordingly. This is another trick, right? Designer, you probably heard of the term called degree of freedom. Have you heard of the term? Degree of freedom. Right? Degree of freedom means that when you look at something, how many degrees are you able to manipulate to change? Right? If you want flexibility, you want as many degrees as possible, right? But flexibility usually bring headache. You don't know which one to track out, right? So it's like this module got how many topics? 12 lecture, right? So if I say there are 12 questions for you to choose, you are going to scratch your head. So flexible. Which one should I focus on? Should I focus on amplifier? Should I focus on current source? Should I focus on system? What covered by Prof. Mao, right? So when you have too many degrees of freedom, you face a dilemma. You don't know how to choose, right? So good thing about degree of freedom, you are flexible. You can do anything. But too much degree of freedom, too flexible, not good. Okay? So in design, we want decent kind of degree of freedom. So usually what we do is, if you see the original gain got so many things, you don't want to keep everything changeable, right? Because it makes your life difficult. I want to design an amplifier that have gain, but you got 10 factors. How do I choose? Too difficult. So instead, what do? You decide, out of all these things, let's make a few that is dominant. GM, dominant, right? Out of all the register, RI2 is limited to the transistor, so let's make it dominant. The other register I can anyhow pick. As long as I pick it big, it doesn't matter. You get the point? So in that case, it limited my choice. From this kind of 10 degree of freedom, eventually I limit to only 4 degree of freedom. Okay? Still flexible enough for me to choose, but it doesn't give me too much headache. Okay? That is one of the key for designing. Common source, same thing, but if you replace the transistor with MOSFET, so if you replace with MOSFET, very likely, MOSFET, looking into it, you no longer have RI. Okay? So therefore, your input resistance no longer have RI. You only end up having RI1 parallel RB1. Out still say the same because MOSFET also have output resistance. And then for the voltage gain, you have the voltage divider followed by current source and then followed by this guy looking 360 degree. Okay? The only thing is you remove the RI and then another current source followed by this resistance 360 degree. Okay? Let's look at the second cases. This is interesting. This is going to lead us to cascode, a very important type, cascode. So for this guy, you are putting a common emitter followed by a common base. It sounds strange. Common emitter and common base. Let's look at input resistance. So for input resistance, it's basically limited by the common emitter stage. So it's RI1. Output resistance, you are going to have RC2 parallel with whatever looking into this Q2. Looking into this Q2 is going to be R02 multiplied by 1 plus GM something. But what is that something? That something is basically what is the resistor connected here, which is RC1 parallel with R0Q1. So that's something over here. Okay? Now, if we do that, the first term usually is much smaller than this guy because R02 is already very big. So in that case, it's simplified to RC2. To find the voltage gain, so basically we don't have any resistor divider. So therefore, we just write away whatever the voltage here convert into the GM cell. So you have GM1, and then you multiply by 360 degree over here. So there is RC1 parallel with R01, parallel with looking into the emitter terminal. You have this guy over here. So this guy you can simplify because RC2 usually is very small. R02 cancel. You got 1 over GM2. And then finally, you have this transistor. So you have GM2 cell again. Multiplied by whatever the resistor looking at this point. You have the RC2 parallel with looking into here, very big. So you can ignore it. So eventually you get the voltage gain. And GM2 cancel. You get this guy. Now, one thing that comes into your mind is that this amplifier seems useless. I use 2 transistor. but the gain is exactly the same as common emitter. Right? Nothing changed. Same as common emitter. If we go through the common source, common gate, same thing. Input resistance, infinite. Output resistance, you look into here, is going to be dominated by RC2. Okay? The voltage gain, you have the GM cell, multiplied by all the resistors here. So R01, RC1, and then this guy. Okay, looking into the source terminal. And then finally, you multiply by this guy, which is the current cell, GM minus GMB. And then finally, what is the total resistor connected at the output point, which is RC2. The other resistor is too big. Eventually, you end up having this guy. Again, 2 transistor, 2 stage, but eventually it gives you exactly the same gain as 1 stage. It seems useless. It seems useless. But there is very unique property for this one is that it helps you remove Mueller effect. It helps you remove Mueller effect. If you remember, what is Mueller effect? Mueller effect is if you have a gain that is like this, and if you have a capacitor that is like this, it will be transformed into this guy, 1 plus A multiplied by C. So what the Mueller effect telling you is that the larger the gain of the amplifier, the worse it is. Am I right? But if you look at this amplifier, the nice thing about this amplifier is that it's split into 2 stages. And what is the first stage gain? The first stage gain is given by GM1 multiplied by this guy, 1 over GM2. Is the gain going to be very big? Let's say I pick the transistor so nice, the GM are equal. This GM cancel. It gives you a gain of 1. Am I right? Right? And this gain of 1 or gain of negative 1, you put it here, it means the capacitor is going to be amplified by 2 times. Right? Instead of 8 times, only 2 times. So we isolate from the second stage. The first stage only see very small gain. And because of this very small gain, the Mueller effect doesn't get exaggerated. But overall gain, still the same as the first stage. Right? So that is the beauty of this common emitter followed by common base. It tries to make use of the small resistance presented by common base and common gate. The small input resistance presented by them to make the first stage having small gain. Because the first stage having small gain, Mueller effect is not being amplified. That is the beauty. And in fact, this can be easily generalized into the so-called cascade. So in cascade, you see, I don't need additional RC1. Why do I need that? Remove RC1. And I end up having this guy, cascade. So cascade. Why cascade? You get rid of the Mueller effect. You have this cap. But this amplifier gain, the output resistance that you see is only 1 over GM. So the gain of the first stage is only GM multiplied by 1 over GM, very small. So the Mueller effect is not exaggerated. Okay, that is the beauty of cascade. And another good thing about cascade, we didn't emphasize it, but you probably notice. You see that the output resistance is R0 multiplied by this whole thing. Okay, R0 multiplied by this whole thing. So you can see that for the cascade, the good thing is that this cascade, it helps improve the resistance looking down into the collector terminal. Boosted by how much? Boosted by this. 1 plus beta R0. Okay? Now, can I put another one? It doesn't help. We go through that before. For BJT, you put another one, it's still going to be stay the same. 1 plus beta R0. So it doesn't matter how many you put. But MOSFET is different. MOSFET is boosted by this factor. So if I put one more, I'm going to have, so for 2 it is R0, 1 plus GM R0. For 3 it is going to be R0, 1 plus GM. So if this guy is proportional to GM R0 squared, this guy is going to be proposed to GM squared R0 cubed. And if you are not happy, put 4 stage, GM cubed R0 4. So any stage that you add, you can boost the output resistance by a factor of GM R0. The limitation, leakage. Okay, eventually, what is your leakage diode current? So that is going to limit how big resistance you are going to get. Okay? So there is the triple cascade as highlighted over here. Okay? So just now we see that for 2, it only improved by GM R0 squared. But with 3, you are going to improve by GM R0 squared multiplied by another GM R0. So overall you have R0 improved by GM R0, the whole thing squared. So therefore it improved by this factor. So any additional cascade you add is going to improve by GM R0. Okay? So this is basically the same as common source followed by common gate amplifier. I'm not going to go through. For the cascade, so for the cascade is a variation of the cascade. We already know the beauty of cascade, but nothing is perfect. If I know from my years of experience with IC design, no solution is ideal, no solution is perfect. Okay, if somebody tells you I have come out with the best circuit, with the best performance, behold, just behold. Okay, there must be something that they didn't tell you. That is always true. Okay, so we really say cascade, good. If you want resistance, boost up, just keep cascading. What is the bad thing? What is the bad thing? If you have so high a ceiling, cascade, no issue, right? I stand on the chair, no, fine. I still have so much room to climb, right? Stack the chair, still got enough. Stack another chair, still got enough. Am I right? But if you keep stacking, eventually you are going to reach the ceiling. Agree? That is the problem with cascade. You can keep cascading, but the voltage of operation just getting higher and higher. Eventually is going to reach the limit. Right? Now, in the old day, that's fine. In the old day, we are talking about 5 volt. 5 volt supply, many room. 3 volt, also fine. 1.8 volt, not so nice, doable. But nowadays is how much? 1 volt. And some people are so ambitious, 0.5 volt. How much room? No room. So what can you do? Folded. That is what folded cascade is. Instead of climbing up, let's climb down. Right? After climb down, climb up again. If you keep doing that, climb up, climb down, climb up, climb down, I can do 4 cascade. Am I right? I can do 4 cascade, achieving same result as having 4 transistors stacking. No issue. Because I just basically climb up, climb down, climb up, climb down. But effectively what you did is transistor connected to the source terminal. The other transistor also connected to the source terminal. Another transistor also connected to source terminal. Except that one is NMOS, the other is PMOS. Another is NMOS, the other is PMOS. You just keep doing this kind of thing. That is folded cascade. So here I just illustrate the principle, only 2. But you can generalize this idea. Okay? Not that difficult. So first stage, we use NPN. We climb up, right? But because of the headroom, we cannot reach. So let's climb down. So using PNP, climb down. And in terms of analysis, still the same. Input resistance, the same. Output resistance, also the same. In terms of the gain, Still the same. No change. What changed? Unlike the stacking cascode, now I always fluctuate around the same voltage. Okay, so for low supply voltage, I'm fine. That is the beauty of folded cascode. So MOSFET, also the same thing. And if you are worried about PMOS, you don't have to worry about PMOS. PMOS, there is no body effect because there is N-well. Now, if you are worried about NMOS, there is body effect, you can use twin-well process. Now, like I say, nobody is perfect. What is the problem with folded cascode? Huh? What is the problem with folded cascode? We love cascode, but we know cascode got headroom issue, so we come out with folded cascode. What is the problem with folded cascode? I told you, you don't trust me. Nobody is perfect. They solve one problem, but they hide the other problem. What is the problem with folded? Come again? More current. In the cascode here, if this consume I, this consume I, what is the total current consumed? I. Look at this guy. This consume I, this consume I. What is the total current consumed? 2I. KCL don't lie. So, what is the price you pay for folded? Power. Nothing is cheap. You guys are more than 21 years old, right? Remember this. You gain something, you lose something. It's always like that. If people tells you, you gain all the thing, you lose nothing, be careful. That's why there are so many people get cheated. Right? Because they think that there is really such thing. You gain something by losing nothing. There is no such thing. Okay? I'm not teaching you circuit, I'm teaching you philosophy. Life lessons. Okay, look at another kind. Common emitter, common collector. Common source, common drain. So, here, common emitter, the input resistance is basically dominated by Ri1, we know already. Output resistance is basically dominated by the second stage common collector, so which is usually very small, 1/Gm. And then in terms of the gain, it just follows the first stage. Because the first stage is the current cell Gm multiplied by the total resistor. Now this guy is a voltage gain. So you usually only lead to unity gain. So the gain is remain something like this. Now how do I figure out the total resistor at the first stage output? So you stand at this point, you look up, you see RC1, you look down, you see R01, you look to the right. Using the BJT reflection rule number 1, you know that is Ri2 multiplied by this factor. Done. Right? Now for MOSFET, same thing. Input resistance, infinite. Output resistance is dominated by the second stage. So you look into here, assume there is body effect. So you're going to have 1/Gm minus GMB. In terms of the voltage gain, you have the current cell, Gm, multiplied by the total resistor because MOSFET is infinite. So you only have RC1 parallel with R01 over here. But in terms of the second stage voltage gain, what you have is this guy. So this guy is not unity. This guy reduced to around 0.8. Okay? So eventually you get the following voltage gain. So this guy is straightforward. What is the beauty of this guy? It's good if you want to get gain at the same time trying to drive a low load. Right? Buffer amplifier is always good to drive low load. Let's say RL of 50 ohm, right? Then you need to use this kind of buffer amplifier. Now this one, I'm cheating. So just now we already reviewed. Common emitter connected to common gate. Common emitter connected to common emitter. Common emitter connected, let me recap. Common emitter connected to common emitter, that give me higher gain. Common emitter connected to common base, that give me cascode. Right? Common emitter connected to common collector, that give me capability to drive low load. Right? These are the three. So now we have looked at the first stage being common emitter. How about first stage being common base? In fact, we notice common emitter, common base, they are very similar. They are only differ by two characteristics. One is gain inversion. So one got negative gain, the other got positive gain. Second, input resistance. Common emitter have moderate input resistance. Common base have low input resistance. That's it. So in fact, we don't have to analyze anything, right? So they are very similar to this guy when you have first stage being common emitter or common source. The only difference, these two things. Compared to them, whatever that we analyze, all still hold valid, except that the gain is positive. And then the input resistance, you no longer enjoy moderate input resistance. You are going to encounter low input resistance. So this kind of amplifier is good if you want to do power amplifier. Not power amplifier. You want to take in the input power, okay? Maximize the input power. So that's good. Your input resistance has to be perfectly matched. Okay. Let's look at this guy. First stage, common collector. Second stage, common emitter. Now, this guy is needed in BJT, but you don't need this kind of thing in MOSFET. Okay, why? Because think about this. The reason why you need common collector as the first stage is because you want high input resistance. You get the point? That is the beauty of common collector. It gives you high input resistance. And MOSFET, common source already give you that. The input resistance is infinite, right? So therefore, for MOSFET, they don't need this kind of thing. Okay? So common collector followed by common emitter, this is very unique, only for BJT. And it later leads to this kind of unique structure called Darlington pair. Darlington pair. You probably heard of this. Okay, but let's go through the normal first, normal amplifier analysis first. So for this guy, input resistance, you can see that it gets boosted, right? This is reflection rule, number one, Ri1 multiplied by 1 plus GM1, whatever the resistor connected over here, which is this guy. So you get boost the input resistance. Output resistance is determined by common emitter stage. So it's basically RC2 parallel with R0 Q2. And then in terms of voltage gain, very simple. Unity gain followed by this guy. So this guy we already know, common emitter. Unity gain followed by this guy. So again, it looks like first stage amplifier, except that it boosts the input resistance seen by common emitter. Okay? If you look at common emitter, the resistance you can only see is Ri. Right? But now, adding a common collector, you boost the input resistance by a factor. Ri multiplied by something else. So that is the beauty of this structure. Now, MOSFET don't need, already mentioned. Now let's look at some tweak variation. Instead of having two-stage outputs separated, let's combine this guy and join it with one transistor, the second transistor. Okay? So right away, one thing you notice, just do a simple analysis. If the current at the input is IB, so this is going to be beta plus 1 IB. The collector current is going to be beta IB. And since this emitter current is the base current for the second transistor Q2, so the second transistor Q2 is going to have beta multiplied by beta plus 1 IB. So approximately beta square IB. The total current is the sum of beta IB plus beta square IB, approximately beta square IB. Right? You have $10,000, you have $1 million. I don't care about 10,000. Right? So that is the beauty. So if you look at the principle of this Darlington pair, basically he is using first transistor to boost the current, and using the boosted current to supply to the second transistor. So effectively, you are having a transistor that improves the current gain from beta to beta squared. That is the beauty of Darlington pair. Okay, so it's using two transistors to make it a super transistor. Okay, from the factor beta, it becomes beta squared. So we can do some quick analysis. Ri is given by Vt Ib, so that is the small signal parameter. So we know Ri1 is simply given by beta Ri2. That is straightforward because the current for Q1 is beta times smaller than the current for Q2. If the current is beta times smaller, of course, the resistance is beta times larger. Right? Straightforward. Now, what is Rin? So Rin, you can use the reflection rule that we derived. It's basically Ri1 multiplied by 1 plus Gm1 and the resistance Ri2. So no trick. But we already know Ri1. Ri1 is beta times Ri2. Okay? We also know Gm1. Gm1 is given by beta divided by Ri1. And Ri1 is actually given by beta times Ri2. So Ri2 cancel, beta cancel. So this ends up having a factor of 2. So effectively, your input resistance is 2 beta times Ri2. 2 beta times Ri2. So Darlington pair not only boosts the gain from beta to beta square, it boosts the resistance from Ri2 to 2 beta Ri2. Okay, sorry. Ri2 to 2 beta Ri2. Okay, so you also boost the input resistance by beta factor. Now, how about the GM? So for transistor, although BJT, we prefer to use the current gain beta, but a lot of time, transistor, you know that we're always interested in the GM. So can we derive the GM easily? So the GM is basically the sum of these two current output. Okay, this current output is depend on GM1 multiplied by VBE1. This current output is given by GM2 multiplied by VBE2. Okay? But what we observe is that when you have V in, this V in will split equally between Q1 and Q2. How do I know that? Because you already noticed your input resistance is given by Ri1, which is due to Q1. How about this guy? This guy is Ri1, GM1, Ri2, which is this guy. But Ri1, GM1, Ri2 is actually given as also, let me see, Ri1. I don't know whether you see that. Ri1 multiplied by GM1 multiplied by Ri2, that is given by beta multiplied by Ri2. But beta multiplied by Ri2 is simply equals to Ri1. Right? So what did I just tell you? The input resistance consists of Q1 and Q2. But these two resistances are the same. Which means any voltage come in, it will be split equally among these two resistors. Am I right? Because these two resistors is the same. Voltage divider. So which means the voltage is split equally, half V in here and also half V in here. Okay? So that is the reason why I put this guy here and why I put this guy here. Now, I don't really care about GM1 because the GM1 is obtained using beta IB. But your GM2 is obtained using beta square IB. So your GM2 is going to be beta times larger than your GM1. So for these two, I can safely ignore this guy. So effectively, your GM is going to be half GM2. Okay? So this Darlington pair, although it's a simple combination of two transistors, but this transistor, if you after combining them, you treat it like a big symbol. So this guy is going to be a super transistor. I draw a very big transistor. But this transistor characteristic, compared to the normal transistor, you have beta square, you have half GM2, and you also have input resistance that is 2 beta Ri2. Okay? You compare to normal single transistor, which has beta, which has GM, and which has Ri. So that is the difference between the two transistors. How to derive the output resistance? Very tedious. If we go through the normal circuit way, we have to replace transistor with hybrid pi model and then try to derive it. So here instead, we try to make use of superposition. So again, as promised, I will show you different way circuit technique that people use trying to simplify the analysis. So what is superposition? Now, the real transistor, if you want to look at the output resistance, basically these two currents will be combined together and you try to apply the voltage source and then you see what is the equivalent current drawn, you can find the output resistance. So in superposition, instead of dealing with the effect that the current going to these two branches simultaneously, let's assume the current only go through one branch. So let's assume current only go through Q1. When the current only go through Q1, we already know what will happen to Q2. The current simply amplified by beta I1 time. So there is one effect, right? Now the second effect, let's assume the current only go through Q2. If that is the case, I can also deduce what is the current in the Q1 branch. So instead of dealing the effect, let's say the current flowing to these two branches, what will happen? Don't do that. Let's consider if current go through this branch, what happened to here? If current go through this branch, what happened to here? Superposition, we combine the effect. That is the principle in this circuit analysis. How does it help us? So first, let's derive I1. Now, I1 can be derived if you know R01. We know R01 because we already derived the equivalent resistance or the driving point resistance looking down into the collector terminal. We can assume there is a resistor connector over here, which is Ri2. Okay? So therefore, R01 can be derived using this reflection rule. I forgot number 2 or number 3. Anyway, I can derive the result as shown over here. And that becomes your R01. After simplification, this is the result. So with this R01, you can actually figure out what is your I1. If you apply a voltage, your I1 can be found. Ohm's law. You already know the resistor, you know the voltage. So this voltage divided by this resistor will give you the I1. If it gives you the I1, you also can deduce what is the beta I1. Right? You can deduce it easily. Now, so this case already solved. How about second case? For the I2, even easy. I2 looking down, you only see R0, 2. So therefore, you can derive I2 very easily. And this also allows you to derive I2 over beta, which is this guy over here. What is the total current? The total current is a superposition. So you just have to add I1, beta I1, I2 beta, I2 over beta, and I2. You add all this current together. This will be the total current contribute to the voltage source that you apply. So we add this guy together, it gives me this. I add this together, it gives me this. Okay? And this I1, I can replace with this guy. And this I2 I can replace with this guy. So eventually I get my output resistance 2/3 R02. It sounds complicated. Yes? But if you spend some time understand the principle, you actually use quite ingenious circuit technique. First, it allows you to derive the current using the driving point resistance, which we just covered. So we can derive the current easily. Second, it shows you how to use superposition ingeniously. Right? You assume one branch current, what happened to the other. You assume one branch current, what happened to the others. Combine them. That is superposition. MOSFET, no need this kind of thing, because this guy boosts the current gain from beta to beta squared. MOSFET even better. He already give you infinite current gain. So there is no need for you to boost. Okay? Common collector followed by common base. So for this guy, input resistance is basically reflection rule, Ri1 multiplied by 1 plus Gm. What is the resistor connected over here, which is given by R1 parallel with 1 over Gm2. So you end up having this guy, which is 2 Ri1. Here I assume IC1 equals to IC2. Not too difficult to understand. This is AC source, so in DC short circuit. So this is also ground. This is also ground. So the VBE here and the VBE here identical. Agree? If VBE is identical, current identical. So I come to the conclusion IC1 equals to IC2. Okay? So therefore Ri1, Ri2 equals to each other. Output resistance, you follow the wire, look up R2, look down. Look down is basically R02 multiplied by 1 plus Gm2. What is the resistor connected at this point? Which is R1, and then looking into here, 1 over Gm1, and also the Ri2. Sorry, where is Ri2? Ri2, sorry. Because there is a resistor, Ri2 over here. So some simplification, you end up having the following. And the voltage gain, you have this guy is common collector, so you actually have the voltage gain, which is given by Gm1 multiplied by the resistor, looking at here, which is R1 and 1 over Gm, divided by 1 plus this guy, so this is voltage gain. And then the second stage is basically a common base amplifier, so you have the current cell Gm2 multiplied by the total resistor at this point, which is 2 R02 parallel with R2. Okay, so that is what we get. For this amplifier, nothing much to say. Nothing much to say. To be frank, if I need common base, usually means I need impedance match. So there is no need for me to do common collector, right? Now, if I want to do using a common collector to drive, I will not follow it by common base. You get my point? Because I already need to boost the impedance. So why do I need to follow by something that impedance is not that big? I should follow directly with common emitter. So this amplifier just analyzed for the sake of it is, but doesn't seem that useful. For MOSFET, same thing, I will skip. Finally, common collector. Again, it's a voltage gain. MOSFET, we just right away covered. MOSFET don't need this kind of thing because MOSFET already have very high input resistance. But for common collector, you can try to boost the resistance larger, okay, using two stages of them, because Ri2, you already boost it one time, and then here you boost it another time. Eventually, it's going to be limited by Re1. But if you pick the Re1 very big, then it's going to be limited by Ri2. Okay? The output resistance is determined by Q2, so it's basically 1 over Gm. And for the voltage gain, very straightforward, it's basically just two unity gain multiplied by each other. So this kind of amplifier, usually you don't need, maybe I shouldn't say, In power amplifier, there is this concept called driving amplifier. Have you heard of it? Driving amplifier. So power amplifier, if you look at it, power amplifier, I want to drive 50 ohm. Usually this 50 ohm end up having a very large transistor. So if you have an audio amplifier directly driving this guy, that is like, how should I say? I have a lorry and I'm driving Mini Cooper, trying to push this lorry. It's not going to work, am I right? But what I can do is, I use Mini Cooper, probably pushing something bigger, maybe SUV. And then the SUV pushing a bigger truck. Okay? So that is the concept. So this kind of common collector followed by common collector, you can consider it is like driving amplifier followed by the final power amplifier. So there is this kind of usage. Very fundamental. Today's topic, very fundamental. I think we still have time, so we can play some game. You guys still have the QR code, right? Do you need to scan the QR code again? Okay. Let me see. Activity 5507, Lecture 2, Lecture 2B. Okay, play. Can you see that? Get ready. Get ready to go home. Oh, scan the QR code. Okay. Done? Okay. We just covered Darlington pair, so this should be quite straightforward. Everything fresh in your memory. Two more students? Probably one more. Two more, yes. Done? How come there are 32? Wow. Go student. Any more? Usually at the time of going home, the amount should drop, not increase. Okay, good. Most of you get it right. I think some of you heard me saying that MOSFET doesn't need Darlington because of the current gate. But this statement is wrong because MOSFET doesn't need, the current gate is infinite. It's exceeding BJT. Okay, not because of the reason it can never exceed BJT. So therefore the last one is wrong. Okay? This is even worse. You don't want to show your name. Okay, second statement. Now got 4 statements to choose. This seems to be harder. Fewer students, complete. QR code again. Okay. It's probably too late. Done? Okay, let's review the result. Why a lot of you think about second one? You didn't remember what I said? Eventually it's limited by leakage. So when you say which statement is true, this means it's universally true, cannot be wrong. So if the statement say output resistance will increase with the number of cascode devices, it means you can just keep adding cascode devices, you will just keep increasing. But I keep telling you, there is a limit. Am I right? You guys fallen asleep. Okay. So only half the class get it right. Okay, that's it. Only have 2 questions. Have fun. So do you prefer this kind of interaction? Okay? Or not okay? If you don't like your name being shown, you can type any nickname you want. Okay? I hate the lecturer, also can. Okay, today's lecture is quite fundamental. I don't believe there is any tutorial related to this one, but tutorial related to the first one is due soon. The second tutorial, I forgot the time due, but after the next lecture. So with that, I'll call it a day. Thanks.